So students, splitting of light beam takes place in this way. When a textile fiber is viewed between crossed Nical prism, the interference occurs. But in absence of a specimen, suppose specimen is not there, then field will remain dark because the polarizer will pass only light which is polarized in one direction, and the analyzer will allow to pass the light which polarized perpendicular to the fiber axis. So suppose one fiber is not there, then light will not split. So the component which is allowed to pass through the polarizer, that will not come up to polarizer. So ultimately at eyepiece the field will remain dark. If a specimen is placed parallel to prism axis, the field will remain still dark because the component of light passed by polarizer will be transmitted without facing any change by specimen and stopped by analyzer. But if the specimen will come at 45 degree of the prism axis, the light will pass by polarizer and fiber will split it into two components. One is X component, another is Y component. And the Y component will have the vibration direction of light and it will transmit at different speeds. So as the light reached to analyzer, the component X and Y in the vibration direction passed by analyzer will be transmitted and field will not remain dark. And in this situation, the field will remain light, and various type of fringes or fringes in one direction will look like that. So transmitted light beam components traveling at different speed will create interference, and due to this interference, fringes of two different color, two different intensity will form in the body of fiber. If the retardation of half a wavelength or an odd multiple of half wavelength, the dark field will change to bright one. When a uniform circular fiber is viewed in monochromatic light, a series of light and dark bands will appear at thickness corresponding to retardation of odd and even number of half wavelength respectively. And these fringes or this phenomena is called as the birefringes. And these fringes are measured, means the at position at which these fringes are formed, the position of polarizer and analyzer is noted. In this way, the birefringes at various positions in fiber appears, and it can be calculated by using this formula delta n 6.18 into phase difference divided by 1000 into fiber diameter micro. Again here pictorially the concept of fringes has been shown. So birefringent crystal between crossed polarizer has been placed here, and this is the white light, this is polarizer which is converting or which is allowing to pass only one component of this light. This is plain polarized light. When it will pass through the sample or through its thickness, then it will break in two components, which you can see here, two components resulting from the birefringes, and here the retardation will take place. So the wavelength of one light is higher and wavelength of another component is lower. So this change in the velocity of light, this will be the measurement of birefringes. How the fringes forms, you can see here with this picture, fringes in textile fiber. In upper one picture, you are seeing the birefringes parallel to fiber axis by extraordinary ray, and it is shown by red color. When birefringes is perpendicular to the fiber axis, and the fringes will form by ordinary ray. So these fringes are shown here by green light. So this will be the birefringes value eta. This will be the ratio between sin I upon sin R, or you can represent this for semi-crystalline material or anisotropic material, delta n equal to T n parallel minus n perpendicular, where T is the thickness or diameter of the material. So fringes forms in one direction when one component, or you can say the ordinary light beam or polarized light, is captured by a polarizer and analyzer. The fringes forms in opposite direction when other component, or you can say the extraordinary light beam or polarized light or component of polarized light, is captured. The fringes forms in opposite direction due to the velocity difference between ordinary and extraordinary light beam. The refractive index of both components is represented as n parallel minus n perpendicular. Birefringence, what is the relation between birefringence and orientation? So delta n or delta eta, this is the value of birefringence. Xc, this is the component of crystalline region. Fc, this is the Hermann's orientation factor or orientation of crystals or crystalline region. Delta and C0 plus 1 minus Xc, this is amorphous content, or the remaining part when you will subtract it from 1. F is amorphous orientation factor and delta and C. So where delta N0C and delta N0A are the intrinsic birefringes for ideally oriented crystal and amorphous phases respectively. Amorphous orientation factor is represented by Fa, and crystalline orientation factor, which is very commonly known as Hermann's orientation factor, is represented by Fc. These are the refractive indices of various fibers. So it is mentioned here for polyethylene 1.550. This is N parallel, and N perpendicular is 1.510. So delta in birefringence is 0.040. Similarly, it is mentioned for other fiber. Here you can see the maximum value for polyester, which is 0.180. Because this is a synthetic fiber, so we can orient the molecular chain in preferred direction, and we can engineer the value of birefringence as per our need. And most of the natural fiber, they have low value of birefringence. It means the degree of orientation of molecular chains in preferred direction is not too much when you will compare with synthetic fibers. So here you can see in case of flax and silk, the value is comparatively high than other fibers. Here in triacetate, the value is negative. So you can see the velocity of extraordinary light that will be higher than the ordinary light. And for glass, both n parallel and n perpendicular are same. So the value of birefringence is 0. It means glass is not a semi-crystalline material. It is a completely isotropic material or amorphous material. So birefringence of polypropylene fiber draw at different draw speed. Draw ratio 6:1, then birefringence value is 0.024. So as the draw ratio is increasing 7:1, 8:1, 9:1, 10:1, and 11:1, the birefringence value has been increased 0.024 to 0.038 when draw ratio has been increased 1:6 to 1:11. These are the refractive index of different species of cotton fiber itself. So here you can see the value will starting for this Vincent, it is a 0.052, and for other fibers, other cotton fiber, it is in decreasing order. So this is the cotton variety which offers the maximum birefringence value. This is just an example to explain if the phase difference of 18 micron diameter polyester fiber is 1100, calculate the birefringence of polyester fiber solution. Polyester fibers. The birefringence can be calculated by using this formula: delta eta equal to 6.18 into phase difference divided by 1000 and fiber diameter in micron. So 6.18 into 1100 divided by 1000, and the fiber diameter in micron is 18. So it will come 0.318 for this polyester fiber. Now we can conclude this birefringence lecture here. The birefringence is an inherent property of many anisotropic crystals like calcite and quartz. Birefringence also develop from other factors like molecular chain orientation, physical stress deformation, effect of applied stress on molecular chain, alignment in polymeric material. Birefringence is the measurement of overall orientation of molecular chain in textile fiber. Overall orientation means the orientation of molecular chain in amorphous region as well as in crystalline region. The birefringence test is a non-destructive test, and it is very commonly used to estimate the overall orientation in different natural as well as in synthetic fibers. So thank you.